work lifting the structure, moving the wide-angle images rectification, unified content boundary modeling, accepted by ICCV2025, and this is our home pages of ConBo-Net. And here's my QR code. You can scan it to contact me. And let's start with the core challenge of wide-angle lines distortion correction. Traditional methods adopt a two-stage pipeline. First, it corrects the distortion, then it rectifies boundaries, just like the upper branch. However, independent optimization leads to error accumulation and misalignment, ultimately degrading image quality. Our key insight is that the same plate spline-based transformation have structural continuity across these two tasks. And this allows us to propose ConBo-Net a single-stage end-to-end framework, like the lower branch, which dynamically learns optimal TPS solution. Our method achieves over 0.6 dB PSNR improvement while avoiding feature blurring in two-stage approaches. And this slide presents ConBo-Net's core architectures, consists of 5 key modules. The first is 2 parallel branches to extract the correction G, like A, which extracts the rectification mesh, and B extracts the rectangling mesh, and C, which is a dynamic deformation attention module. It generates rigid maps via spatial attention regions. And the flow requirement module uses high-level features from VS-Net 8, which utilize as a backbone, and it outputs to the module E, which is a TPS differential transformation module, which generates the final result optimized jointly by 4 losses: appearance losses, perception losses, ordinal geometry losses, and B-spline losses. The ordinal geometry losses is critical here. It enforces curvature monotonicity based on wide-angle camera physical pairs, mitigating distortion parameter estimation areas. And begin the final working results. You can see this like the ground truth. And this page shows qualitative comparisons between ConBo-Net and state-of-the-art two-stage methods. When compared horizontally to combinations like DeepCalib and DRGAN, our results excel in 2 aspects. First, semantic integrity linear structures, like the rows, building edges, are restored more accurately. Second, boundary regulatory. The output naturally maintains the rectangular boundaries and aligns closest to the ground truth. This validates the advantage to single-state joint optimization. No need to split tasks, balancing geometric fidelity and boundary regularity within a unified framework. To verify generalization, we tested distorted images from real-world wide-angle lenses, including GoPro, Optica 6.5 mm, and Sensing 10mm f3. As shown, ConBo-Net effectively restores a scene geometry regardless of lines type. For example, correcting twisted buildings, straight lines, and rows into linear structures. The output's geometric appearance is closer to real-world scenes, demonstrating that our model is not limited to synthetic data distributions. It adapts to diverse lines distortions in practical applications. This slide consolidates quantitative comparisons across whole image quality metrics and downstream task performance directly from our benchmark. Table 1. First, core image quality, ConBo-Net outperforms all two-stage methods across key indicators. The PSNR, which is 18.64 dB for the best two-stage method, DRGAN plus RecRecNet indicating superior pixel level fidelity. SSIM keys 0.54 versus 0.51 for DRGAN plus the RecRecNet. And SSIM reaches 0.65 versus 0.60, confirming stronger structural preservation. And second is downstream task gains. Beyond image quality, we translate corrections into tangible performance lifts for region models, like the SAM segmentation 6.6, 0.56, mIoU, and the YOLO detection 0.64 MAP and 0.65 mIoU. Besides that, our time achieved is the least time, and it only uses 0.04 second to achieve a photos test. This balance of speed and accuracy validates our end-to-end design's practical value. The core value of wide-angle image correction lies in empowering reliable downstream region tasks, and we validate ConBo-Net on two critical benchmarks: the SAM-based segmentation and YOLO object detection. Starting with SAM segmentation, as marked by red arrows, two-stage pipelines like the DRGAN and RecRecNet fail in complex scenarios. Their split optimization causes blurred segmentation masks and misaligned edges. In contrast, ConBo-Net end-to-end framework outputs marks that tightly align with target boundaries, preserving semantic integrity. For YOLO detection, two-stage methods introduce geometric inconsistencies that lead to missed detection. For example, small traffic signs or bounding dots misalignment. Our corrected imaging resolves this, ensuring detectors capture objects accurately without distortion introduced errors. We further dissect these inherent flaws of two-stage methods. The leftmost is pure correction within regular boundaries. The second from left is two-stage rectification, showing obvious resolution detection and the content loss. ConBo-Net the rightmost, which is ours, and it directly outputs a unified, corrected, and rectified result, with no resolution loss and no boundary color misjudgment, or the white or black boundaries misclassified as semantic information by rectification models. This is because we directly learn motion representations from correction to rectification, skipping redundant intermediate steps and minimizing information loss at the source. Finally, we objectively address the limitations in extreme radial distortion. For example, the image as regions, slight residual distortion remain in linear boundary structures. This arises because strict geometric consistency and rectangular boundary regularity conflict under extreme conditions. Our future work will introduce fine-grained motion representations like the local dynamic TPSGs to elevate this trade-off. In summary, ConBo-Net achieved this sought-out performance in wide-angle image correction and rectification via the single-stage joint modeling, physical prior integration, and dynamic attention fusion, providing higher quality inputs for downstream region tasks. Thank you.